Hi, welcome back. Today we're going to talk about the cutting edge world of multimodal AI, and very specifically, we'll be talking about vision transformers, which are revolutionizing the way machines understand and interpret images. If you have come across Meta's AI glasses, I'm sure which you have, we are exactly going to talk about the underlying technology behind these glasses, and one step further, we will be even attempting to build one. So let's see how it goes. So on the right, we have the transformer architecture, which was originally released by a set of Google engineers on 2017 for language translation purpose. But because of this multi-hit attention, it has gained a lot of popularity and could be applied in so many use cases. So we're going to be discussing about one such use case today, which is image captioning. So when I give this image, I want my model to understand all the hidden relationship between this image and the caption. And when given a new image, I want my model to come up with new predictions of captions. So the original dataset looks something like this. On a hugging face, we have some random picture. And for each picture, we have 5 captions. A man sleeping on a bench outside with a white and black dog sitting next to him. A man lays on the bench, blah, blah, blah. And we have around 31,000 of these rows. So for sake of simplicity, I took only 2 images and 2 captions for each. And I also want to see how the model is learning and how the numbers are moving in each of these layers. So to reduce the complexity, I have took a smaller data structure. But once we are comfortable with that smaller data set, all we need to do is swap the data set with the bigger one and train it for multiple days on GPU. So let's see how the code goes. But even before going into the code, if you look into this architecture, it kind of beautifully explained what happens in every single step, but still, there are some hidden underlying complexity inside each block, which is not explained in this image. So I went ahead and I created one for myself. So which is basically this. So on the top, we have the encoder. On the bottom, we have decoder. I kind of flattened it. So it kind of beautifully explains all the hidden complexities in the model. And also I have included the shapes, how it changes in each section, and if we are applying some values, and how does these values change. So I try to visualize this, and I kind of put a screenshot there, so it's more intuitive than a normal picture. So let's see what's happening in every single step before going into the code. So let's say we have an image of random size 512 by 612. So we convert this image into a square 224 by 224. So once we have a square, we create patches. Let's say I created this 4 patches here, 2 by 2 grid. So each patch has 112 by 112 pixels by 3 channels. So the final output will look something like this, 1 by 4 by 37,000 something. So this 37,000 is the numerical representation of each patch. So I don't like this number, it's too big. So I'm kind of squeezing these numbers to 6 by passing it to a feed-forward neural network. So you could choose any number of your wish. So reality, we would choose 512 or 1024. Even ChatGPT had 12,000 embeddings, but I'm using only 6 because I want to visualize the data in a better form. So once we have the embeddings, we kind of create positional encodings for each patch, and then we add it to form the output. So this output will be the input for our encoder layer. So all this purple block on the top. So let's see how the positional encodings are made in the first place and why they are made. Let's say we have 2 sentences. The first one is, I will be present tomorrow. The second sentence is, will I be present tomorrow? So I'm just swapping the first 2 words, and you can clearly see it has changed the context of the sentence. So when we represent the data in a numerical form, we are not representing the position of the data. We are only representing the individual tokens. So somehow, I want to also include the positional information into this embeddings. How do I do that? So the easy way is to come up with the numbers 1, 2, 3, 4, 5 for each word and add these numbers to this. So that's what we've been doing in the past. So if you see the output, it doesn't look good. So it's kind of unevenly distributed. So the longer the sequence, the bigger the number gets. And the difference between the initial token and the last token gets so huge. So this model will be completely unfit to learn. So that's why we came up with the intelligent idea of using sine and the cosine waves, which you can see in this picture. So we create sine and the cosine waves for how many dimensions we want. and we kind of slice in for every given position, every given token, and we take those. So if you see on the first position, we are taking this one. On the second position, we are sliding here and we are taking these values. So these values are kind of stagnant between 1 and -1. So these values are not going anywhere above this one. So these form a unique set of numbers which can be used to represent the positional information. So these are the formula to calculate that. I will also show in a code how to do that. So which is basically, yep, this one. Yep, this one beautiful function. So basically we calculate the denominator and then we calculate the position using sine and cosine. And then we stack it, we flatten it, and we adjust it to the shape that we want. So we have our input encoded like this, and then we get the positional encodings like this fashion, and then we add this both, we get this output. So straight away, if you compare the positional encoding with the normal numbers, you can see sine and the cosine has represented the data in a more decent fashion. So that's why we go for cos and sine positional encoding. So that's the intuition. So let's go back into the encoder block. So we have the input data ready, so which we keep a copy to add it to our residual block later. And then we pass this input into a feed forward, which kind of throws out query, key, and the values. So in the original paper, they have given individual linear layers, but you can also put it in one linear layer, and you can change the output to be 3 times the input. So it's pretty much the same. So once you have the QKV, it looks something like this. You can also see the data on the down. So then it's ready to go into the multi-heads. So you basically take the query and multiply it with the key. So even before that, you kind of split these embeddings between the multiple heads. So again, for the simplicity, I didn't split anything. I kept only one head. So this is just for visualization purpose. So you take the query and multiply it with the K transpose. You do the dot product, you get an output of 1 by 4 by 4 fashion. So basically this 4 by 4 refers to the context window. So nowadays Gemini has a 1 million context window. So if you want to have a bigger context window, then you need to play with these numbers. And since I have resized my image, I'm not applying any padding here. So there is no need for padding mask. So the output is finally going through a softmax to give a probability distribution between 0 and 1, and finally multiplied with the values, dot product with the values to get a final output. So once out of the multi-head layers, which is kept for parallel processing, parallel computing, faster computation, however you like to call it. So it's to reduce the time complexity and to learn faster. And once out of this multi-head attention, we concatenate all these outputs, and then we add the residual block, which you have kept as a copy in the beginning, and the final output goes through the layer normalization. So inside the layer normalization, we calculate the mean standard deviation. So let me show you in the code. Yep. So this is all happening. So we calculate the mean, we calculate the variance and standard deviation. So we subtract the inputs with the mean and divide it by the standard deviation, and we add 2 learnable parameters, gamma and beta. So which are basically inherited from n dot module, and this would be our output. So once out of the layer normalization, it again goes to the feed forward. We're also keeping another copy for residual connection, and we kind of extracting 128 dimensions from 6 and kind of squeezing back to 6 again. So this is kept for a reason, because once coming out of the multi-head layers, we kind of concatenate this data, but these data haven't learned between themselves. So we kind of pass it to the feed forward to make this data learn between themselves. So, and finally we retain the shape and we add the residual tensor, and it goes through another layer normalization, and that's our final output. And if you see the output, it's in the same shape, 1 by 4 by 6 as the input. So this process could be repeated multiple times. So all the purple block on the top could be repeated 5 or 6 times before going into further processing. So to capture the rich data, rich representation of the data. So basically these would be our keys and values for the decoder layer, which we will be talking in a minute. So decoder is quite complex compared to the encoder. So here we have words. We add start token to the caption, and we add padding to the maximum to fill in the maximum sequence length. And it goes through an embedding layer where we create embeddings of same size. So these dimensions should match with the image dimensions. So we can have different patch size. Here I have 4 patches. It's totally fine to have a different number because it will be taken care automatically in the calculation in multi-head part, which I will show you. And we create positional encodings and we add this to add this to get X. So once we have the X, we keep a copy to add it to the residual connections, and we pass it to the feed forward 3 times the output, and we get Q, K, and V. And finally, multi-head retention part, where you send in the data, you split the embeddings between different heads for allowing it to do parallel computation, and you multiply the query with K transpose, and you get an output. Then you add 2 masks. So this is one of the important part of decoder. So where you add look ahead mask and padding mask. I would suggest go for the look ahead mask in the beginning. So this is the mask, and this is once you apply the mask. And it goes to the softmax to give an output. And then we create a padding mask, then we apply the padding mask. So I initially tried to add this diagonal mask and the padding mask at one go, but when I come here, the bottom values are all 0. So when I do a softmax, it gave me NaN values. So the problem persisted. So I kind of printed out every single line to see. And the easy way to overcome this problem is to apply the diagonal mask first, do a softmax, then apply the padding mask. This will avoid the problem of NaN values. And the final output, if you see, all the diagonal values on the top are removed. The final layer, which is actually padded layer, the rows and columns are removed. So the final output is in the way that we want it. So I'm happy about it. And then we pause it. Yeah, we multiply dot product with the V. We get an output. And once out of the multi-heads, we kind of concatenate all these values. We add the residual tensors. Then it goes through a layer normalization to get the Q. So for the masked multi-head cross attention, we get the key and the values from the encoder, the query from the decoder itself. So if you see, the key and the values are coming from here. And if you see the dimensions, there is something important you need to notice here. So if you see the query, it has 5 words and each word has 6 embeddings. Here we have 4 patches and we have 6 embeddings for each patch. So that's totally fine, which will be taken care. So we will be multiplying, doing a dot product query with K transpose. You get a final output. No need of applying the mask here, which we already did. And we get a final output, and we go to the softmax, multiply it with the V, get an output, concatenate it, add the residual tensors, and it finally goes through a layer normalization, and again another feed forward to learn between the multiple heads, and you get a final output. So since this is of the same fashion as it went in, you can also repeat this decoder block multiple times before proceeding further. So basically in the original paper, they have it around 8 times, 6 or 8 times. So finally you pass it to the feed forward, and this time the output is in the shape of the total vocabulary size. So in reality, it would be 50,000 or 60,000. So then you do the softmax to split the probability between these 50,000 words, and at a time you're predicting 1 word. So we don't need to do this because it's kind of sufficient, comfortably taken care inside cross entropy loss, which it will do the softmax inside. So it's pretty much pointless, I thought, doing it here. So then you calculate the loss and you backpropagate to reduce this loss. So that's all happening here. So when you backpropagate, it goes all the way back and all the way back in the encoder to learn all the learnable parameters, and it updates its weights. So that's all happening in the vision transformer in a higher level. So once you have a strong understanding and a grip of what's happening in a higher level, it could be much easier when you go to the coding part. So I would suggest not directly go into the code because there's roughly around 500 lines of code. It might be a bit overwhelming. At least it was overwhelming for me. So what I would suggest is go through these files. I will provide a link for these files in the GitHub. So where we have positional encodings, and I have given some random values to play with, and you can pretty much get an idea of what's going on here. And we have some file for multi-head attention, so you can have clear idea of how the data is split between multiple heads and how the output is coming out and how we concatenate it. And we have something for self-attention and we have something for layer normalization. So once you're comfortable with that, then it's good to go into the transformer. So yeah, this is a function to process the data. Our data is processed in the form that I showed in the image. I took 5 as my maximum sequence length, so input tokens are converted and target tokens are converted, and I've created a mask. So these are the things that I've pre-processed. And the breakdown is pretty much simple. We create embeddings for the encoder, we create embeddings for the decoder, and we create positional encodings for both. And again, all we left is encoder, decoder, how many times we want to repeat it. And then finally, feed forward and softmax. And we calculate the loss and backpropagate. So that's all we'll be doing. And these are some of the utility functions. So this is a scalar product. So where we will be applying the attention mask and the pad mask, and defaultly it's set to be false and none. And only when we activate these layers, these codes get activated. And we have something for positional encoding again. So basically you're applying torch.sign to which position you want, the first position, third position, and the fifth position. You apply odd values, and for the rest you apply even values, and you stack it, flatten it, and ensure that it's in the same shape as your inputs. So we have something for multi-hit attention. So since we will be using this multi-hit attention in both encoder and the decoder, with slightly small difference in the mask, I kind of created one class, only one class for it. And we have something for layer normalization, which we will be reusing. And on the encoder, we have a position-wise feed forward. So this would be unique because we have some learnable parameters here. And on the encoder, this is where the magic happens. So we get the X, we pass it to the attention, then we get a dropout, we add it to the residual and apply normalizations, and then we do repeat the process. So sequentially is to basically tell how many times I want to repeat this encoder process, and one class for encoder to represent all this functionality. So on the decoder, it's pretty much the same, where we have an additional function, multi-hit cross attention. So basically this is this one. And yeah, it pretty much does the same thing, but in a slightly different fashion. So we get the query from the decoder and the key and the value from the encoder. So we're just ensuring that it's happening in the right form that we want. It's like few lines of code that you need to change here, that's it. And for the decoder layer, it's pretty much the same. It passes the self-attention, then you do the normalization, then it passes through the multi-hit cross attention, then you do the dropout. Yep, and sequential layer to repeat how many times you want. And the final function that kind of encompasses all this codes above. So a final class for transformers, where we have defined all the necessary things, where we pass in the input and we do the encoding for the input. We create embeddings for it, and we create positional embeddings, and we add those two, and then we pass it to encoder. Nothing much happening here. And for the decoder, the same. We're creating the tokens, and we're creating embeddings for the token, and we're creating positional encodings for those tokens. And we're kind of adding those two, and we're sending it to the decoder layer, and rest is taken care of. So we are instantiating the model with some really basic parameters, just with the intention to visualize what's happening inside the code. And we have the dimension set to be 6, and the number of heads, multiple heads I want is 1, and drop ratio is 0.1. I want only 10% to be eliminated. And the feed forward is 128. Yeah, the basic stuff's here. And this is actually the architecture of the model. So one decoder and one encoder. And here's the interesting part, the training. So here you can clearly see what is happening in every epoch. So we are sending in the input data in this fashion. We're creating input tokens, which is basically, yeah, so input tokens, we're creating mask for it. And so when that starts, when the transformer starts, this is the first step that's happening. We're creating embeddings for the inputs for the image first, and then we create positional encodings, and we add it, and we can like compare it. These numbers are supposed to be what it is, what it should be. So yeah, so it kind of explains what's happening, how QKV is created, and what happens in the attention part. So if there is any mask that has been added, it will also be mentioned here. So you can comfortably see if a mask is added in the encoder or decoder or not. So for encoder, we don't want any mask to be applied. So we can just ensure that if it is applied or not, and the final values of the dot product. Yep. So you can like pretty much go through every single thing. So the one interesting thing I would like to show is the masking part of it. Yep. So on the decoder, we have some diagonal mask created. So the diagonal mask is applied, and then we apply the softmax. So the values change between zeros and ones. Then we apply the padding mask, and after application, the data looks something like this. And we have some values, and yeah, so the decoder is done. So we're doing the multi-hit cross attention, and yeah, that's pretty much all here. And I'm finally saving the model, and I'm kind of reloading the model, and I'm continuing the training from where I have left. So I have assigned a new variable without transformer. So when you're running that code, just make sure that you're training on the new variable, and also you're predicting on the new variable. So that's why wherever you're starting from wherever you left. So not from scratch again. So this was quite comfortable for me when you want to train for a longer duration. And if your mission crashes, you don't want to lose anything. So just want to grab at least what you have learned. And in the inference part, it's pretty straightforward. We send an image. The image looks something like this. So what's happening to the image is basically we are pre-processing the image. We're converting it into right shapes, splitting into right patches. And yeah, you can pretty much see it here. Yep, so the patch size is the same that we have trained for. And we are sending the input token. The input token is actually nothing in the beginning, and we just add the start token and we send it. And every time it runs this decoder, it kind of predicts one word, and it kind of appends this generated caption list. So, and you can pretty much see what's happening in every single layer. And finally, we can see every time it updates, and you can see the final output here. Yep, so the predicted output for this time is 6, which is a token value, and kind of added to the list. And this is your final predicted output. So you use tokenizer to extract the data, and this is my prediction. So it doesn't make sense, obviously, because it has been trained only on 2 images, and the maximum vocabulary size was something like 15. So if you train on at least 1,000 images with decent caption size, the prediction will be good. So that's what I'm trying to do it now. So I'm planning to rent a GPU, and yeah, so I'm planning to rent a GPU and train for overnight, and let's see how the model predicts. But for now, the code looks perfect on a small data set, and all you need to do is to just swap them with a bigger one. So I will put the link on the description. Feel free to check it out.